everybody for your response. So before we begin, I would like to introduce the speaker for today's session. So today we have the instructor as Mr. Ajit here with us, and he's the applications engineer at COMSOL. So before we move into the session, before I hand over the session to Ajit, I will let you know few instructions. Everybody will be on mute during the session. So if you have any questions, please type them to the questions tab. We will try to take as many questions as possible today. And but if any of your questions are unanswered, you can join us for the Q&A session on Monday at 3 p.m. IST. So yeah, and also we'll be sharing the assignments with you. So to access the assignments, we'll be emailing the passcode of accessing the assignment today after this session, and you can also find that pass key for accessing today's assignment in the handouts section. So there is a in your GoToWebinar this dashboard, you will see a handout section where you can see there is one PDF file. In that PDF file, you will have a link where you can download the files which are required for today's hands-on session, and you can also find the passkey which will be used to access the assignments. Okay. So after this session, we'll be sharing the recording of this particular session. So with this, I'm going to hand over the session to Ajit. Ajit, can you please take over?
Yeah, thanks, Anushka, and good afternoon, everyone, and welcome to the third day of the training course. So this course is about this session is about meshing techniques in COMSOL multiphysics. I'm going to talk about various techniques which you can do to mesh your geometry, and also how you can perform various mesh convergence criteria and so on. Okay, so before we move ahead, I just wanted to know that I hope you have all gone through the Learning Center links which we have shared with you before the training course. Because if you have not gone through those training courses, I'm going to give you a short recap of the meshing part, and then we will move to some problem solving. So the agenda for this session will be to explain you about what is meshing, give you a short recap of various options which are available, and then we will be taking these 3 examples to see that how we can improve our meshing and what are the things you have to take care while meshing various problems. Okay, then I will cover how you can model truncating domains. So such as if you have, let's say, infinite domain, or if you have perfectly meshed layers. So if you want to include them in your model, then I will explain you what things you need to take care while meshing those domains. Okay, then I will cover the contact meshing. So let's suppose that you're working on a problem where you need to simulate contact between 2 bodies, 2 or more bodies, and there what kind of meshing considerations you need to take care of. Meanwhile, if you have any queries, feel free to type them in the chat box. So my colleague Nitish is also along with me as moderator, so he will be helping you out with some of the queries. Okay, yeah, someone is complaining about the sound is not clear. Let me know if this is the case with everyone. Can you hear me clearly or not? Okay, so I think most of them have replied that they are able to hear me well. So you need to check your part. Yeah. So now regarding meshing, first of all, what is meshing? So the idea behind a finite element method is, let's suppose that you have a partial differential equation. Okay, and now you want to solve this equation in a particular domain. Let's say this is your domain. and you want to solve this partial differential equation in this domain. Okay, now this domain is bounded by some boundary conditions. Okay, so there could be some boundary conditions, and if you are solving a time dependent problem, then there could be some initial conditions as well. Now we need some technique, right, to solve this equation in this domain. So finite element method is a numerical technique which we use to solve our PDEs in a particular domain. And how we do it? We divide our domain into subdomains. So I'm dividing this domain omega into small domains. So this could take any shape. So there is no restriction regarding the shape of these subdomains. Okay, so these domains are nothing but your subdomains. Okay, let me just erase it. Okay, so what we do is we divide our full domain into these subdomains. We also call these subdomains as elements. In the finite element terminology, we call them these subdomains as elements. Okay, now you can see that there are these number of elements which are being created here. Now these elements, if I just draw these elements separately, like let's say these are the elements which are being created. This is, let's say, element number 1, element number 2, and element number 3. Now these elements are interconnected at these junctions, you can see, right? Now these junctions are nothing but, these are known as nodes. In finite element terminology, we call these junctions as nodes. So currently I have considered linear elements, so therefore these are connected at these nodes, but you can get some nodes at the center of these elements as well. So that is a separate part. I will come to that in a bit. Okay. Now, when we are solving our partial differential equation using finite element, what we are doing is we are solving the solution at these nodes only, at these nodal points, because it's a discrete way of solving your equation. You're not solving a continuous equation in the domain. You're solving this equation in a discrete form. So when I say that it's a discrete, in a discrete manner, this means that I'm solving this equation onto these nodes. Okay, so like here you can see this portion. In this portion, I will just draw it here. Now here there is an arc here which is being present here. Okay, and there are these two nodes. And let's say that this is a triangular element, and this is what it looks like, this portion. Okay. Now, when we are solving this equation, the solution which we are getting will be at these nodes only. It will not cover this curvature part. It will only cover these nodal points. Let's say this nodal point is I, J, and K. So you are going to get the solution at these 3 points only, not on this curvature. Okay. Now to capture or to get the solution at this curvature part, what we will do is we will try to increase the number of elements. That is one way. We increase the number of elements. That I can also say that I decrease the element size. This is another way of saying the same thing. Decrease the size of the element. And second is I can increase the shape order. So I will talk about the order part. Increase order of the elements. Okay. Now, sorry. By decreasing size, I means I will take more number of elements so that enough number of elements are present to capture this curvature. Because it's not the geometry which the software is reading, it's the mesh. Okay, so this geometry is just for our purpose. I mean, just for our visualization purpose. But inside the software, software is reading only the mesh part and not the geometry part. So if you have enough number of elements to capture this kind of curvature behavior, then you can say that it is very well approximating the shape of your boundary. Therefore, meshing is important. Okay. Now we talk about different kinds of elements which you can use in a software. So let's say that I'm just drawing here two different kinds of elements. So one is a linear element and this is a triangular element. Okay, I'm just drawing the same thing here as well. These both are the same things. So now I will make a distinguish between these two sections. Why I'm drawing these two. So first one is, I will call it as a linear. Okay, and this one I'm calling it as quadratic. Now I've already explained you that the solution which we get from finite element is at these nodes only. Now what happens in the middle? Because if you consider a single element, you know that you have got a solution at node I, node J, and node K. But now what happens in the middle between these nodes? Because whenever we see a finite element plot, we see that it's a colored plot, a very nice graphs and so on. But behind, you can see that the solutions are obtained only on these nodes. So at the middle portion of these elements, the solution is obtained via interpolation. So all those results are interpolated. Okay. Now to capture these interpolation functions, we also call these interpolation functions as shape functions. To get the result between these nodes. Now here I have mentioned two kinds of interpolation function. One is linear and this is quadratic. Quadratic doesn't mean I'm going to draw a quadrilateral. It can be quadrilateral, but this quadratic and linear means these are the interpolation functions I'm talking about. For example, if I just write a linear function, it will be like y equals to mx plus c. So this is a kind of a linear function. And if I want to write a quadratic function, it could be y equals to ax square plus bx plus c. You can see, you can make a distinguish now, right? That what is a linear function and what is a quadratic function. So these linear functions can bend only in two ways. So if I consider this line element with two nodes, it can bend either in this way or this can bend in this way. There are no other possibilities of bending this particular element. It can either turn this side or this node can go this side. So that is one of the property of these shape functions. Okay. Now, when I talk about quadratic functions, similarly, I'm considering the same two-noded element. Here you can see that what happens when we use quadratic shape functions, additional node is added at the center of this element, and this enables this element to form a curvature like this, like a parabolic curvature, or it can bend now. Okay, so there are various possibilities. One possibility is this one. Another possibility could be this one. Another possibility could be this one. So it can bend either in either ways. Okay, so now there are two things which I have talked about. So one thing is the element size. Second thing is order of the elements. Order I will call with these interpolation functions, which is a shape function or the shape order. Okay. So in any finite element software, you have the option where you can reduce the mesh size. So when you reduce your mesh size, what you are doing is you are capturing the geometry by increasing the number of elements. The second option to capture your geometry is you can increase the order with the same number of elements, which will enable extra nodes between those two nodes, and it will also allow you to have a curvature kind of phenomena. Because if you try to have more number of linear elements, you will require extremely large number of linear elements to capture a curvature, whereas you can use less number of quadratic elements to capture the same curvature. Okay, so with this I will just explain you how you can set up your meshing in COMSOL. So I will just give you some basic guidelines. I'm opening COMSOL now. I hope you can see my screen. Now in the model wizard, I'm just selecting a 3D domain. I'm not worried about the physics as of now, so I will just escape this part. And now I'm moving to my COMSOL GUI. I hope you are familiar with the whole GUI here. You might have worked with some problems in geometry in the last session and so on. So I'm going to create a cylinder. Okay. Now, after you have created your geometry, next thing is I will mesh it. So now once I go to mesh, so there is a sequence type which is physics controlled, and also you have the option to have a user controlled sequence. So I will come to that, what is the difference between these two, but let me just go with this physics control. Now I will select this build all option, and you can see that a whole grid, I will say this grid has been created to capture this geometry. This grid is known as mesh. Okay, there are different elements which are being created here to capture this particular physics. Next is you have the option to select the element size. So here there are different options. If you want, this is the normal mesh by default, but if you want to, let's say, want to increase the number of elements to make the mesh more finer, you can opt for different options and you can refine your mesh. Okay. Next, let me coarse it, because some places you don't want the solution to be more accurate, then you can select a coarser mesh, and you can see that although your geometry was cylindrical, but this mesh doesn't look like cylindrical, but the solution which you are going to get will be on this mesh only. Okay, now if you want to, like, this was a physics control mesh, which was kind of a predefined options by the software. But now let's suppose that you want to control the mesh according to your own requirement. So what you can do is you can select the option of user control in that case. Okay, and you can see that as soon as I've selected this user control option here, this pre-tetrahedral node is being created here. Okay, which means that this mesh was developed with pre-tetrahedral elements. Now these tetrahedral elements, how they look like, I will just show you. So you have this triangle, and then there is a point at out of plane, at some distance out of plane, and then these vertices are being joined here like this. So this is the tetrahedral element. Okay, similarly you will have quad element like this, which will be used to capture your domain. You might also have prism kind of elements like these ones. Okay, so all these different kinds of elements you can have in the software. So let me go back to the model. Okay, now here you can see that these elements are tetrahedral elements. Now let's suppose I want to control the meshing on the surface of this cylinder. So what can I do is I can right click on my mesh, and you will find all the relevant options of meshing at this point. Okay, you just need to right click on these nodes and you can get the option to, modify the meshing, specify different kinds of meshing and so on. Now under more operations, you have the flexibility where you can mesh your subdomains. Subdomains in the sense, in this case, your main domain is a 3D domain. Okay, it's a 3-dimensional domain, this cylinder. But let's suppose that you want to go one domain below this. So those entities can be selected by the more operations option here. Like the one entity below this domain option is your boundary. Okay, and one option below boundary is your edge. Now let's suppose I want to have some different kind of meshing onto the surface of this cylinder. I can select that option by going to more operations, and here I can select this free triangular, and I can click on build selected. You can see that it's a, although it is a circle, but it looks to me like a polygon because of the meshing. Now if I increase the number of elements, let me make it fine. Now you can see that it is a circle, but now we have enough number of elements to capture those geometric effects. Okay, so this way you can create your different kinds of mesh on a local level. Now at each node here, which you are seeing, you always get an option to change the size of that particular entity. For example, here I have created a free triangular mesh, and let's suppose that I want to change the size of the mesh for only the surface. Then I can right click on this free triangular node and I can select size. Now there are two size nodes here. You can see that the first size node under the mesh one, this is the global size node. So this controls the global size of your meshing. Whereas if you select these size under some sub nodes, then these size nodes control the local size. For example, this size node will be limited to controlling the size of only this entity. Okay, so what I can do is I will show you that I can make it an extremely fine mesh on the surface, and then I can create a free tetrahedral mesh. You will see that apart from this, the size here, you can see the remaining size is being taken off from the global size node. Okay. Now under size node, I have shown you the predefined sizes as of now. This is extremely fine, extra fine, finer, normal, coarse, coarser, and so on. But now let's suppose you want to have a different size than what is being predefined here, because there could be instances where you want to go to a size which is much smaller than this one. Because here by predefined, using the predefined option, you only get the option to go maximum up to extremely fine mesh. But now if you want to have any other size, you can just click on custom, and here you can define the maximum element size. So by currently using the extremely fine mesh, you are getting a size of 0.04 meter, but you can further reduce it. I will make it 0.02, and you will see that it will take much more time to discretize surface, but you will see the effect of doing that. You can see now the size has reduced, and the maximum element size has become 0.002. Similarly, the minimum element size, the maximum element growth rate. So the growth rate represents how well the elements are getting increased or getting propagated in a progressive manner. For example, this will give you the ratio of the element length to the element length which is adjacent to the previous one. Which means that if the size of the first element is, let's say, 1 meter, the next element will be 1.3 times of the previous length of the element. And that's how this element grows from various boundaries. Then next is the curvature factor, so which will give you the option to have enough number of elements to capture the curvature. The lower the value is, the more the elements will be there to capture the curvature. And if you have very thin slits or very thin narrow gaps, so those you can control by using the resolution of narrow regions. Okay, so right now I have used a free triangular mesh to capture the top surface, but let's suppose I need to have a quadrilateral mesh, a quad mesh on the top. So what I can do is I can delete this option and I can go to free quad. Always remember, you have to finalize your mesh with either free tetrahedral or with swept. So only these two options are available to finalize your meshing. If you remember, while you were creating geometry, the option to finalize was form union or form assembly. Likewise, here you have to finalize your meshing with either free tetrahedral or with swept, either of these two. Okay, so therefore I'm always moving this option to the end, option of this free tetrahedral. Now let me create a quad mesh. You can see now I have created this quad mesh here, and the remaining will be tetrahedral. Okay. Now some people are having some difficulty in applying those options. So I will again repeat it. You can right click on mesh. You can also clear, first of all, clear your mesh completely. You can clear by selecting this delete sequence. Using this, you can clear your mesh. And now you have to go to more operations. Under more operations, you have to select free triangular. So earlier I did using free triangular mesh. You can see that these nodes, whether these nodes are coming, you are also getting the same sequence in the meshing or not. You can just tally from my plot here. Okay, so then it will asking you which boundary you want to mesh with triangular elements. So I have selected this top boundary. So this top boundary number will be shown here, and then you can click on build selected. Okay, next is, because I have to mesh the remaining part of my geometry as well. So I told you that either you can use swept or you can use free tetrahedral. So free tetrahedral mesh we have already seen how it looks like. Now let us see what happens when we choose swept meshing. So once I select swept meshing, you can see that now I'm having a structured mesh. Instead of those random tetrahedral elements, now I have a more structured mesh, which means that this surface is getting repeated after each of these intervals. Okay, and any day this mesh is much better than free tetrahedral mesh. So I will tell you why. First, let me know if you are getting this or not. Okay, someone is getting error message like the face is locked by adjacent domain mesh and cannot be remeshed. So I told you that the last option in your meshing has to be either swept or free tetrahedral. So what we have done is you might have had this free tetrahedral on top of free triangular. You have to drag it down to the end. Once you drag that option down to the last, and if you build your mesh, it should be okay. Okay. So currently the mesh which you are seeing with this free triangular, this is a surface mesh. But now using this swept operation, I have created a volume mesh. So these two options which you are seeing here, free tetrahedral and swept. These two options generate a volume mesh. So therefore I told you, whenever you try to finalize your meshing, always use either of these two options. Either you can use swept or you can use free tetrahedral. Swept is going to give you a more structured mesh. So let's suppose that the way the element, the your geometry is propagating from the surface is like in a continuous manner, then you can use swept meshing. Otherwise, if you want to capture your geometry with some kind of meshing, then you have to choose free tetrahedral. Okay. Now you can see that you can relate the kind of elements which are created now. So if you pay attention, you can see the elements. I told you that they are getting repeated now at each of these surfaces. So if you consider one element, you will see that this element looks like a prism element, like this one. So there is a triangle like this, and then there are these edges, and on the bottom face also you are getting a triangle. So it looks like a prism element. You can pay attention now onto the geometry here. So it looks like this mesh. I'll just show you. Okay, now you can easily relate with this mesh. Okay, so now let's suppose that you want to have a pyramid kind of element, or if you want to have a quadrilateral or a brick element, then what you can do is, instead of triangular mesh on top, you can pick a quad mesh. So again, I'm going to more operations, free quad. I will drag this option. You can see I'm dragging this option on top of swept, and here I'm selecting this top boundary. Now I'm having a quad mesh, and I will sweep it around, and you can see that now I have a more of a brick element. I'm getting few queries. Why is the bottom of the cylinder having free triangular? Didn't you select only the top surface? I told you that when I selected the top surface, that top surface mesh was getting repeated at each interval. So when it is getting repeated, at the bottom also you will see the same mesh, because that mesh is getting repeated. So that's the idea of a swept meshing. You are sweeping that mesh across your whole domain. Okay. Yeah, I will come to that point, that why which mesh is better and why to select this mesh and that mesh, and at which place which mesh is better. But right now you first get an idea how you can apply this meshing. Okay. Now for each these subnodes, I showed you that you can control the size of the element. Okay. But now let's suppose that you want to decide the number of elements as well. So in the size, you are able to say, okay, the size of the element has to be at 0.1 mm, or it could be extra fine or fine. So that way you are selecting the size. But let's suppose you want to have, let's say, 5 elements in a particular section. That you can control by applying distribution. Okay, just below size node, you will get a node of distribution. And here you can see that there are 1, 2, 3, 4, 5, 6, 7 number of elements along the Z direction. But if you want to have 10 number of elements, you can apply here 10 number of elements, and if you build it, you will see that 10 number of elements will be created. Okay, so the difference between this free tetrahedral and swept is, in free tetrahedral you are getting a free meshing. Okay, this mesh is not bounded by anything. That is only bounded by the size you are giving, and it will try to capture your physics with some random shape elements. I mean, those will be tetrahedral elements, but with a random number of distribution. But if you want to have a better control of the meshing, that control you can get by using a swept meshing. So which will create a more of a structured mesh like this one. Now, which is better? Next question arises, that which mesh is better among these two? So to analyze that, let us do this a quick comparison. Okay, right now I am choosing a normal mesh. So in my global size node, I have selected normal, and remaining I am just removing all these size nodes. So with a normal mesh and a free quad mesh on top, you can see in the message box, you will get all the information regarding the steps which you are taking here. Like in this case, when I created this mesh consists of 640 domain elements, 416 boundary elements, and 84 edge elements. So you can see the last line. This is my final operation which I performed on this mesh. Okay. Now let us create a free tetrahedral mesh. So what I will do is I will disable these two options. You'll see that I am disabling these two options, and now I am creating a free tetrahedral mesh here, and I am building all. So now I have a kind of a random free meshing. Okay, there is a random mesh now. It's not structured in any way, and now you can see the number of elements which are created now. So now, if you compare the last two lines, previously it took like 640 domain elements, 416 boundary elements, and 84 edge elements. But with this free tetrahedral mesh, I am getting 6,211 domain elements and 832 boundary elements, which means the mesh number of elements in the mesh has increased approximately 10 times. The more number of elements you are going to have, the more number of degrees of freedom you are going to solve, and your model will be more heavy. Okay, you will require more computational resources in terms of memory, in terms of computational power, and time as well. So it is always preferable that if you are able to create a structured mesh in your model, that is the best way to mesh your structure. Okay, that is I will say more of an optimum way to mesh your structure. Okay, so depending on whether to use triangular mesh or a quad mesh, so let's suppose that you have curvature present in your geometry, so those curvatures are captured better by a triangular element rather than a quad element. So if you have some curvature, like here you can see this, there is a curvature here which is present in this model. So for these, you can mesh the top surface with triangular elements, and the remaining part you can sweep it. So I will do that now. So first, let me just remove these three nodes. So I will show you what I mean. So best way to mesh such kind of geometry is you can first do a free triangular meshing. because these triangular elements are really good in capturing these curvature effects. Okay, and then you can sweep it. Now you can see that although the number of elements which are created are more than the one which was created by quad mesh, when the quad mesh was present on top, but still the way the curvature has been captured will be better here. Still, this is 6 times less than the one which is created with a free tetrahedral mesh. So that is one of the main difference when you try to mesh with a free tetrahedral mesh and with a swept meshing or a structured meshing. Okay. Yeah, so with this I will just give you some assignment now just to work upon. So these are the two exercises you have to do now. So I will give you 2 to 3 minutes to solve these two exercises. So in the first exercise you can see that very coarse, there is a plate here with a hole at the center of this plate. The mesh at this region, you can see the mesh is very fine in this boundary. Okay, with this boundary the mesh you can see is very fine. In the second case, this is case 1 and this is case 2. So in the second case you can see that the overall mesh is a bit finer than the previous one, and at the center here you can see the mesh is very fine, and even at this edge also you can see that the mesh is fine. Okay, so you have to solve these two exercises. So I will give you like 2 to 3 minutes to do that. You can use the same geometry to do both the exercises. Okay, and then I will demonstrate you how you can do that. So I'm getting a few queries like, is it advisable to have a free triangular mesh throughout the geometry? Actually, it all depends on the curvature. If you have curvatures in your geometry, then of course you have to use triangular elements. But that is not the optimum way of meshing your geometry. If you have the option to have a swept meshing, then always prefer the swept meshing. Okay, that is any day that is a better option to pick. Meshing is finer only at one corner of this block, not at all the corners. Only this one corner. So how the curvature factor and narrow region option work? Yeah, so curvature factor will determine you how much number of elements you want to have in a curved boundary. So it will not work for a straight boundary, but if you have a curved boundary, what it does it computes the radius of the curvature of that boundary, and then it will calculate the length of the element, and then it will divide it. So if you use a smaller value there, if you use the value close to 0, then you will have more number of elements to capture the curvature. Okay, so now I hope you have tried this. Or shall I give you another minute? So I'm getting few more queries. If we choose default option for meshing, what are the drawbacks? So if you choose default option, of course it is going to mesh your complete domain, but that won't be the optimum way. I told you that if you use free tetrahedral mesh, it was creating 10 times more number of elements than if you create it by controlling the mesh by yourself. And there could be regions where you want to capture, let's say, some gradients near the walls, things like that. So that in that way you need a more user control kind of meshing. Okay, so I will just build this exercise now. Okay, so now I'm opening a new instance of COMSOL 3D and so now I'm just creating a blank template for you. In this, there is a block here. I'll just put the height as 0.2. Okay, and now I will create one cylinder of radius 0.2. Let's say x will be 0.5 and y will be 0.5. So I have this cylinder, and now I will use the difference option to subtract this. So now I have got that block in place, and now I'm going to create the meshing. So for the meshing, I told you that the meshing was very fine at this hole for the first exercise. So if you want to control this subdomain kind of task, you can go to more operations, free triangular, because it was a triangular meshing. And now I will select these boundaries. Okay. So you can see that I have selected these boundaries, and these the number of the boundary numbers are being appearing here. And I will use a subnode to set the size, because the size of these the size of mesh for these boundary is less. So I will pick size here and I will make it extremely fine like this. Okay. And now the remaining portion, I told you that you have to always finalizing the mesh with either swept or boundary layer or free tetrahedral. So in my case, I don't see it is a swept mesh. It is just tetrahedral elements are everywhere. So I will pick a free tetrahedral. And I will click on build all. So this mesh is a bit finer. I can make it coarser, size, and I can make it extra coarse, even it is extremely coarse. Yeah, so you can see that I've got a similar kind of meshing, which I showed you in my slide. Okay, so someone tried to use swept meshing and error will come. Error will of course come because you need to have a regular mesh in order to do a swept meshing. So here the mesh is already created at the center, but the geometry is not like that. If you want to have a swept meshing for this particular case, what you can do is, I'm just removing these nodes. So if you want to create a swept meshing for this case, first you have to mesh the surface. Let's say you mesh it with triangular elements like this, and then you can do a swept meshing like this. Okay, so first you have to mesh the top surface and then you have to do it the swept, because swept you have to do it in the third direction. It's not like it will create swept for every case. So you need to have a regular kind of geometry to create those swept operations. Okay, one part was to do a fine mesh at this boundary, so that I will also show you how to do that. You have to go to more operations, and here you will get edge option. Select this edge option and select this part, this edge here, and you can control the size of this edge to make it extremely fine. Now this swept will not work because it's not a regular geometry anymore. So I will create tetrahedral. You can see that now I have a fine mesh here at this edge. Okay, so I'm getting some queries while using free tetrahedral for the entire geometry. Why does the elements appear smaller near the center and larger as we move away from it? I told you there is an option here of maximum element growth rate, which means that the size of the element next to the adjacent one will grow with a factor of 1.5. So if the size of the element here is x1, so the next element size will be 1.5 times x1. Like that it will grow. Okay, so this is controlled using the maximum element growth rate. Okay, so we are running out of time. Actually, there are these things should have been done with the learning center videos. So this is one more exercise. You can try this exercise later. So this is the classical exercise for performing a swept meshing. Okay, so here you have to create a cone and you have to perform this exercise. Okay. Now I'm going to demonstrate you how you can figure out that how many elements are enough for capturing your geometry. So what I'm doing is I'm creating a circle of radius 1. Okay, so this was all the part of the learning center videos. If you have not gone through them, and you have to go through them again, and you will understand how all these steps. Okay, so now I have created this circle here, and let me mesh it. Let me mesh with a extremely coarse mesh. So while meshing with a extremely coarse mesh, you can see that instead of a circle, I'm getting a kind of a polygon. Okay, the area of this circle has to be 3.14 up to order of if I just say that up to the order of 2 digits. So the area has to be pi r square. So radius is 1. So my area will be pi r. Okay, let us see how much area is there, how much area software is computing now. So to see that, I am just right clicking on mesh, and here I am selecting statistics, and you can see the mesh area, 3 meters square. Okay, which means that there is a lot of approximation this mesh has done to the solution. Okay, next in this mesh statistics you get a lot of information, like there are various quality measures here, like skewness, maximum angle, volume versus circumradius, and so on. Right now the quality measure is based on the skewness, and here you can see that the minimum element quality is 0.6744, average element quality is 0.7826, and element area ratio is 0.4, and mesh area is 3 meters square. And below that you will find a histogram here, where you will see that element quality in terms of how the element quality is being distributed across the different elements. Okay, now this average element quality, if it is, I will say, if it is above 0.8 or 0.85, it is considered to be really good. And if the number of elements, these black color lines, if you are seeing, if these lines are more inclined towards the right side, okay, if you have more number of elements coming in the right side, then that overall mesh is considered to be good mesh. Okay, now let us, what we will do is we will try to refine the element size. We will try to reduce it, let's say, to finer. So now I have changed my element size to finer, and again I'm going to statistics, and now you can see that my mesh area is 3.139, which is still not 3.14 something, but still it is pretty close. And the number of elements you can see now they are being uh, getting accumulated at the right side of the histogram, and the average element quality is now 0.88, which is considered to be really good, okay, for most of the problems. So if you want to learn more about these quality measures, I will advise you can go through our manual. So there you will find all the information regarding how these different quality measures are computed. Okay, so this mesh is basically, which I am showing you, this is capturing the geometry. But now what about physics? Because physics also needs to be captured, right? So currently, yeah. So currently, what I'm showing you is how we are capturing the geometry part. But now say that you are applying any physical and any physics on this geometry. You can specify the physical idea as well. For example, if you are solving a dynamic problem that has like let's show you. Let's say that you are solving a dynamic problem where you want to capture the wave in your model. Okay, let's say solving an elliptic equation, and the way of equation is a problem which you want to capture. And let me draw the wave which needs to be captured. Let's say that is the smallest wavelength in your model which needs to be captured. The y-axis corresponds to the amplitude, and x-axis corresponds to the spatial distance, and calculated as x. And this is lambda, which is the wavelength of your wave. Okay. Now let's do this step by step. Now let's take two number of elements to calculate this wave. So if I take two elements, it will be one element like axis and the second element like axis. So this will be element number 1 and this will be element number 2. Okay. Now you can see that if I use this number of elements, I am not able to capture the spatial behavior. Which means this number of elements are insufficient to capture the dynamic of my problem. Okay. Now let us use the number of elements. Let us increase it to 4. So if I increase 4, it will look like this. So this will be 1, 2, 3, and 4. Let me put as over it so that I can distinguish between my various new numbers and these new numbers. Okay, so now I have 4 number of elements, which means I will say that it is getting some behavior in my solution. I will not say behavior, but at least I am getting some amplitude of this wave at these points as well. Right. Now what about changing the order now? Because I have 3 number of elements, and I say that around 4 elements are I will say decent enough to capture this wave activity. But how about changing the order now? So these are linear elements, but if I make elements as quadratic, so what it will do is it will introduce one more node at the center of these elements like this. Okay. And now these elements can get bent. So these elements have this kind of information. If you remember, I told you initially that if you have linear elements, you have one bending like this and like this. Whereas if you use these quadratic elements, will have a node, and now you can bend elements like this. So you have this curvature factor which can be counted for when you use the interpolation between these nodes. So that's what is happening here. So whenever we solve this kind of dynamic problems, we use a criteria like you have at least five. So we don't rely on four. We just say that if you have at least five quadratic elements, quadratic element. This is not quad element. This is quadratic shape function. Okay, quad element per wavelength. So that is sufficient to capture this wavelength of dynamic behavior. So first we calculate the wavelength, and then we say that this wavelength has to be, the element size has to be, let me find size with delta x. It has to be at least lambda by 5. Okay, it has to be lambda by 5. Sorry, yeah. Okay. So this session is recorded. If you want me to some repeated things, and you can watch this session, because I have a lot of things to cover, and it won't be covered if I have to repeat a lot of things. Okay, so this exercise I already demonstrated you that when you have a circle of radius, and if you evaluate the area, you can see that if you refine the mesh, you are basically converging the geometry part. Okay. Now for a dynamic problem, you can see that if you use less number of elements, like here you can see this is the example of a double slit experiment where there are two slits here and a wave is propagating from these slits. So generally what happens is once this wave passes out from this outlet, so there is a interference which occurs and you see a dark line and a bright line, then dark line and a bright line onto the screen. So that's the whole phenomena of this double slit experiment. But here you don't see that, and from this solution you don't make out anything. But if you refine the mesh according to the wave which is going to propagate in this system, then you will see the perfect interference pattern here. You can see this dark lines and then bright part, then dark part, then this bright part, and so on. So therefore, this is very important to capture your geometry as well as you have to capture your physics as well. Okay, so now let's take our first exercise. So in this case, what we are doing is we have a channel. Okay, and in this channel we have an inlet and an outlet. So this is our model, and we can exploit the axisymmetry of this model. So we are considering only one axisymmetric model of this system. So this again reduces your model size significantly. And now we will do a mesh convergence study onto this model. Okay. So one guy asked me that delta x has to be less than or equal to. So the element size, the minimum element size has to be that one. You can further reduce element size, you will get better results, of course. But the minimum element size has to be lambda by 5. Okay, you cannot go for element size which is higher than lambda by 5. So for example, lambda by 5, if you get a size of let's say 0.1 meter, you cannot go for 0.2 meters. You have to go either 1.1 or 0.09, less than that size. Okay, so for this exercise, I will advise you to open COMSOL. Okay, just open a new model. And now you have to open this non-Newtonian flow model. So we have already shared these models in the handouts. So I hope you have downloaded these models, because we are not going to set up the physics today. We are going to work on the meshing part. So this model will be required as a base model, and we will work on the meshing. Okay, so open this model of non-Newtonian flow basic. Let me know if you are facing any difficulty in finding this. So I will wait for a few more seconds. So if it is opening in read-only mode, it's fine. You have to just at the end you have to save this model as a save as option. You have to use the save as option to save it with a different name. That is perfectly fine. Okay. So let me just go through this model first. So this is the model of a laminar flow. Okay, where there is a inlet at this particular boundary. So we have provided some inlet pressure at this top boundary here. Okay, and at the bottom we have this outlet boundary. Now this red color line which you are seeing, this is the line of axisymmetry. Okay, so now what we will do is we will try to first mesh this problem. Now the idea is like once the flow will be happening here, so at this bottleneck which you are seeing here at this center, so there the velocity will be very high. Okay, and the gradients of the velocity will be high also as well. So we need to capture those phenomena. Okay, we will see that how many elements are enough to capture our physics accurately. So this is the kind of a mesh convergence study which we are going to do in this model. Right now you can see that I have explained you about the user control mesh, but now when a physics control mesh is being set up, then you don't worry, you don't need to take care of small details. For example, at the wall boundaries, if you are familiar with some basic fluid mechanics, you might be knowing that near the walls, if there is no slip condition, there the velocity is zero. And just near to these walls, there are very high velocity gradients because of the viscous boundary layers. Okay, now if I am meshing it to capture those boundary layers, you will see that very small boundary layer meshing is being done here. If I zoom this boundaries, you can see that a boundary layer mesh is being created here. So this mesh is parallel to the to the surface about which this mesh is created, and this is very helpful in capturing the high gradients near the walls. At the top also you can see that you will find these boundary layers. Okay. Now what we will do is we will start with a normal mesh. So just select normal from the element size, and in the label also write normal, so that we can track that we have used a normal mesh here for this case. Then click on build all, and you will find a bit coarser mesh which is created. Next you have to go to study one, in the study one also, you have to write here normal in the label, just to track our results for comparison. Okay, you can write here normal, and now you have to compute it. Okay, we got some solution, so it's okay for now. Let us solve this problem again with a different mesh. Okay, so to add a new mesh, you have to right click on component 1 and select add mesh. Okay, right click on component 1 and you can click on add mesh. So you will see that mesh 2 will be created under normal. Now in the mesh 2, right here course. Okay, the label this mesh 2 as course. Last time we labeled it as normal. Now we are labeling it as course, and from the element size, select extra course. Okay, select extra course and build all. You will see that a very coarser mesh will be created now. Now we are going to add another study so that we can compare our results of normal study with the study with coarser mesh. Okay, so I'm going to click on study on top on this ribbon, and you can click on add study. Okay, in the add study, you have to select stationery. Okay, and you will see that in the stationery study, you will get this mesh selection. In the mesh selection, make sure that coarser mesh is selected. So you have an option where you can run your model with different mesh also. So make sure that a coarse mesh is selected here, and in the label also study to write coarse. Like last time we have written normal, so now we will write here coarse. And compute it. Yes, in the meshing we have selected extra course. I'm just naming it as course just to save time. That's it. Okay, so we have got this results from extra course mesh as well. You can see that here I've selected extra course only in the meshing, and I've got another set of results using extra course mesh. Okay, next we are going to create another mesh. So again, follow the same procedure. Go to component 1, select add mesh, and this time select a extra fine mesh. Okay, now select an extra fine mesh. In the label also you have to write extra fine, and add a new study where you have to run this study with the extra fine mesh. Okay, it is automatically selected. Okay, so it's not, I'm not selecting course here, so it's by the label I'm calling it.